Have you ever wondered how to write efficient and maintainable code? Well, my friend, allow me to introduce you to the SOLID principles. These are not just random words, but an acronym that stands for 5 principles that, when followed, can make your software architecture easy to manage, maintain, and scale. First up, we have S for Single Responsibility Principle, which encourages each component of your program to have only one job. Next is O for Open-Closed Principle, which advises us to write code that is open for extension but closed for modification. The L stands for Liskov Substitution Principle, a rule that ensures objects in a program can be replaced with instances of their subtypes without altering the correctness of the program. Then comes I for Interface Segregation Principle, which suggests that no client should be forced to depend on interfaces they don't use. Finally, D for Dependency Inversion Principle, which promotes high-level modules not to depend on low-level modules directly. Stay tuned as we delve into each principle one by one, starting with the S in SOLID, which stands for the Single Responsibility Principle. In the world of software development, it's common to come across complex classes that seem to be doing too many things at once. This is where the Single Responsibility Principle comes into play. It's a simple yet powerful concept that states, a class should have only one reason to change. This means each class should be responsible for a single part of the software's functionality, and that responsibility should be entirely encapsulated by the class. Let's illustrate this principle with an example. Imagine a class that handles both user authentication and user data access. It might seem convenient to have everything in one place, but what happens when you need to change how user authentication works? You're not just tweaking the authentication process, you're modifying a class that also governs data access. This could potentially disrupt the data access functionality and introduce bugs into the system. Now let's think about this from another angle. What if we separate these two responsibilities into 2 distinct classes? One class can handle user authentication while the other takes care of user data access. With this approach, if the authentication process needs to change, we only need to modify the authentication class. The data access class remains untouched, reducing the risk of inadvertently introducing errors. This principle encourages us to break down our code into smaller, more manageable parts, each with a single purpose. It's all about creating modular and maintainable software. When each class has a single responsibility, it becomes easier to understand, easier to test, and easier to maintain. By following the single responsibility principle, we can avoid a tangled mess of code and instead create a system where each part does one thing and does it well. It's like having a well-organized toolbox, where each tool has a specific job. You wouldn't use a hammer to screw in a bolt, would you? In essence, the single responsibility principle encourages us to break down our code into smaller, more manageable parts, each with a single purpose. And next up, the O in SOLID, standing for the Open-Closed Principle. This principle is a key part of good software design and states that software entities, whether they be modules, classes or functions, should be open for extension but closed for modification. But what does that mean exactly? Well, let's break it down. When we say a software entity should be open for extension, we mean that its behavior can be extended to cater to new demands. That is, new functionality can be added as the demands of your application grow and change. On the flip side, when we say that the same entity should be closed for modification, we mean that once the entity has been developed and tested, the code can be put to bed. It should not need to be tampered with every time there's a new requirement. In essence, adding new features shouldn't entail altering tried and tested code. Now, let's illustrate this principle with an example. Imagine we have a payment processing system that supports credit card payments. Business is booming, and now we need to add support for mobile wallet payments. In line with the open-closed principle, we wouldn't want to dive into our existing working and tested credit card payment code to jam in some mobile wallet functionality. Instead, we should design our system in such a way that we can add this new payment method without disturbing the existing code. So we create a new module or class for the mobile wallet payment, extending our payment processing system's functionality without modifying the existing credit card payment code. This approach ensures that our existing code remains untouched and less prone to new bugs, while we can still add the new features that our growing business needs. The open-closed principle, therefore, promotes the idea of writing code that is flexible to accommodate new requirements without changing the existing code. This principle encourages us to think ahead and design our systems to be scalable and resilient, helping us to deliver robust and maintainable software. Moving on to the L in SOLID, which is the Liskov substitution principle. This principle is a key pillar in object-oriented programming. It essentially states that if a program is using a base class, then the reference to the base class can be replaced with a derived class without affecting the correctness of the program. To illustrate, imagine a rectangle with a width and a height. Now consider a square, which is a type of rectangle, right? But here's the catch. A square always has equal width and height. If we substitute a rectangle with a square in a program that modifies width and height independently, we could end up with a square that's not really a square. This violates the Liskov substitution principle. This principle is crucial because it ensures that a subclass can replace its superclass without causing any anomalies or issues in the functionality of the program. The Liskov substitution principle thus ensures that a subclass can replace its superclass without causing any issues. Now let's discuss the I in SOLID, which stands for the interface segregation principle. This principle is all about making sure that clients, or in simpler terms, users of a system, are not forced to depend on interfaces they do not use. It's about keeping things clean, tidy, and efficient. Imagine you're at a buffet. You wouldn't want to have to pay for the entire spread if all you're going to eat is the salad, right? Similarly, in the world of programming, we want to ensure that users only pay for what they use, so to speak. Let's illustrate this with an example. Consider a printer. Now, a printer can perform a variety of tasks. It can print, scan, fax, and even photocopy. These are all different functionalities, and not all users will need all of them. Some might only want to print, while others might want to scan as well. If we were to bundle all these functionalities into one massive printer interface, every user would be forced to depend on the entire interface, even if they only use a fraction of its functionalities. This would be like forcing someone to buy the entire buffet spread just to eat the salad. It's inefficient and, quite frankly, a little unfair. Instead, what we could do is segregate the printer interface into smaller, more specific interfaces. We could have a separate print interface, a scan interface, a fax interface, and a photocopy interface. This way, users who only want to print can depend on the print interface and ignore the rest. They don't have to concern themselves with functionalities they don't need. This is the essence of the interface segregation principle. It's about creating smaller, more specific interfaces so that users only have to depend on what they actually use. It's about efficiency, tidiness, and above all, user satisfaction. The interface segregation principle, therefore, encourages us to split our interfaces into smaller, more specific ones to ensure that the clients use only what they need. Finally, we have the D in SOLID, which represents the dependency inversion principle. Now, this principle is all about dependencies and how they should be managed in a system. In simple terms, it states that high-level modules should not depend on low-level modules, but rather both should depend on abstractions. Let's break this down. High-level modules are the ones that give your system its identity. They define the core operations that your system performs. On the other hand, low-level modules are the ones that provide the building blocks for these operations. They are the nuts and bolts of your system, if you will. Now imagine a scenario where a button controls a lamp. In a traditional setup, the button module would be directly dependent on the lamp module. Press the button and the lamp lights up. But what if we want to replace the lamp with, say, a fan? We'd have to rewrite the button module, wouldn't we? And that's hardly efficient or flexible. This is where the dependency inversion principle comes in. It suggests that both the button and the lamp should depend on an abstraction. In this case, we might create an interface called switchable device. Both the button and the lamp would then depend on this interface. The button would send a switch on or switch off command, and the lamp would respond to it. If we want to replace the lamp with a fan later, we'd only need to ensure that the fan also implements the switchable device interface. No need to touch the button module at all. By doing this, we can make our system more flexible and adaptable. Changes in one module don't necessitate changes in others. This is the power of the dependency inversion principle. It fosters the idea of decoupling software modules, which is a key aspect of writing maintainable and scalable code. The dependency inversion principle, in essence, fosters the idea of decoupling software modules to achieve a flexible and adaptable system.